Okay, everybody, here we are. We are taking a look at, now what section are we in? This is 5.2, the definite integral. Section 5.2, the definite integral. So let's cross out this word, and not yesterday because we don't have class every day, but before. Before, in section 5.1, we use rectangles, that is Riemann summations, to estimate the area under a curve. And we saw that, well, it made sense to us that if we used more rectangles, we would get a better approximation. And that if we use infinitely many rectangles, we would get the best approximation. So what we're going to do is we're going to come up with a formula or an approach, an algorithm, if you will, that'll help us calculate that area under the curve using a large number of rectangles more quickly. Now, in order to do that, we're going to have to use some sigma notation. Sigma notation is a summation notation. I'm going to zoom in on this. And basically what it says is, take the sum of a bunch of terms of a sequence. Okay? Now, this is the sequence. These A's here represent the terms of the sequence. The subscript tells you which term of the sequence it is. So A sub 1 is the first term of the sequence. A sub 2 is the second term of the sequence. When you perform a summation of a sequence, what you're essentially doing is you are finding the sum of a bunch of terms. What I mean by that is you're going to take the first term, A sub 1, plus the second term, A sub 2, plus the third term, A sub 3, and stop at some point. Here we designate that stopping point as the A sub n. This is the mathematical shorthand for that. The capital letter sigma, that's that big E looking thing there, that's going to be the one that tells us what we're going to do. We're going to do a summation. Now, the thing on the bottom below that big sigma is going to be our indexing variable, I, and our lower limit for our summation. The thing at the top is going to be the upper limit for the summation. And so what this tells me to do is it tells me to go find the sequence with terms named A, start with the first term of the sequence, stop when I get to the nth term of the sequence, and then add them all up. Okay? So let's take a look at what that looks like. What would this mean to do? Well, there's our sequence. So these are the A sub i's. Start with the first one, stop with the 36th one. So this means start with the first term, and I'm going to do it in light blue, which would be 3 times 1 plus 4, because the I says start at 1, and then add to that the second term, which would be 3 times 2 plus 4, and then add to that the third term, which would be 3 times 3 plus 4, and then I'm going to keep going, and when am I going to stop? Dot, dot, dot. I'm going to stop when I get to the 36th term of the sequence. So 3 times 36 plus 4. And that's what I would do to find the sum of this sequence. Now, personally, I don't want to do that because that, to me, seems like a lot of work. So what I would rather do is I would rather simplify that by using some simple properties of summation. Now, I say simple, I do not mean easy. I just mean uncomplicated. Here's our first couple simple, uncomplicated properties. The first one reads, and I'm talking about this one right here, the summation of k times the sequence is just going to be equal to k times the sum of this sequence. So you see what happened there? A constant times the sequence, the constant gets pulled out in front. And then what does the second one say? The second one says that if you have the sum of two sequences added together or subtracted from each other, that you can rip that summation apart and write it not as one summation, but as two summations that are then properly added or subtracted to match. So what I'm going to argue is we should do that down here so that I don't have to figure out 36 different terms of the sequence and then add them all together, and that we should use those two properties and turn our original summation into this summation. 3 times the sum as I goes from 1 to 36 of I plus the sum as I goes from 1 to 30. Whoa, why did I write 34? To 36 of plain old 4. Now, why would this be easier? Well, if we think about what this now means, this first summation right here means 3 times 1 plus 2 plus 3 plus ... plus 36. The second summation here means plus 4 plus 4 plus 4 plus ... plus 4. And there's going to be 36 of those guys. So we can quickly add this up now because we know some tricks to do this. The second summation over here, that's clearly just going to be 36 times 4. This one is going to be 3 times 36 times 37 divided by 2. And then we'll just add those two together. At this point, I'm just going to do a little bit of math in my calculator over here. So I have 3 times 36 times 37. Oops. Yeah, times 37 divided by 2. So this is 1,998. The oops wasn't that the math was wrong. The oops was my fat fingers doing something wrong on my calculator. And then plus 36 times 4. And I get 144 for a grand total of 1998 plus 144. I get 2,142. And so the summation is 2,142. Now you might be wondering how I did one piece of that. Okay? I don't think that you should be asking about this, nor this, nor this turning into that. 3 is clearly there. You might have a question about this, and that's because I learned something, and I'm hoping you did too, that says that if you want to add up a bunch of numbers, the quick way to do it is to take the first one plus the last one, multiply it by how many you have, and divide it by 2. This is the 37. Right? Carl Friedrich Gauss came up with that somewhere around like age 9 or something. I don't know what the story is, something about busy work in school. Right? But summations. I hope that you're seeing where this is going. We're going to find a way to write adding up all the rectangles as a summation. Here's what it leads us to. It's going to lead us to using summations and using those summations to find those areas of those rectangles under the curve. Here are the formulas we're going to need. These are summation formulas, and what you should notice about them is each of these formulas allows you to remove the summation from the situation or from the expression. Right? We just got done using this one. We did the summation as I goes from 1 to 36 of 4, and we found that that was 4 times 36. So I'm going to draw some arrows here to make those connections. 36 was the N, 4 was the C, and what's the answer when you do a summation from 1 to 36 of the number 4 a whole bunch of times? It's 4 times 36. We also just did number 2 here. We did the summation. Well, I don't want the arrows anymore. Silly me. We did the summation as I went from 1 to 36 of I, and we said that that was 36 times 37 divided by 2. Right? And then draw some arrows again. N plus 1 divided by 2. We haven't looked at the other two yet, but the other two simply say that if your summation, if you can somehow reduce your summation, so the argument of the summation is simply I squared, you can replace it with this formula right here, n times n plus 1 times 2n plus 1 divided by 6. And the last one over here says you can change I cubes into n squareds, n plus 1 squareds divided by 4. Right? Also, to make this work, we need formulas for left endpoints, right endpoints, and midpoints for our sample points. So each of these are our sample point formulas, that is, left and rights, rights and lefts, and midpoints. Right endpoints, the x sub i's are always a plus I times delta x. Left endpoints are always a plus I minus 1 times that delta x. And midpoints are always a's plus I minus a half times delta x. Now, if the problem doesn't tell you which one to use, which one are you going to use? I'll say it again. If the problem doesn't tell you which one to use, which one are you going to use? And the correct answer is, I am going to be lazy as possible and use rights. Because look at the formulas again. Which of those formulas is the least complicated? And so you always want to work with the least complicated formula if possible. So we use the right point because we're lazy and it's the easiest. All right, so what I would like to do is I would like to use summation notation. I'm working on example number 1. I would like to use summation notation to write out the approximation of the area under the curve f of x equals x squared plus 3 on the interval 0 to 4 using 8 rectangles and right endpoints. So I'm just going to start copying down to things that I know. I know that a is equal to 0. I know that b is equal to 4. That tells me then that if n is equal to 8, that our delta x is going to be 4 minus 0 divided by 8, which reduces down to 1/2. Right? Since they asked me to use right endpoints, I know that my sample points, my x sub I stars, are always going to be a plus I times delta x. But I know values for all those now. I can say that a is 0. I know that I is I. I know that delta x is 1/2, or if I want to clean that up, it's just I divided by 2. That my sample points, my x sub i's, are I divided by 2. Right? Now I need to take all of this, as well as my function, and write it as a summation. So over here on the left, I'm going to write that summation. It is going to be a summation as I goes from 1 to 8. Okay, why 1 to 8? 1 to 8 because I have one rectangle and then I have 8 rectangles. So I start with the first rectangle and I stop with the 8th rectangle. And then the formula that's going to go right here is going to be the formula for calculating area. Well, the area of a rectangle is height times width. So we've got our sample point in the function times our delta x. So let's go ahead and fill in that even more correctly. We're doing the summation as I goes from 1 to 8 of, let's see, what was my function? Oh yeah, it's over here. So I need to drag this down here, but fill in the x with the x sub I of I over 2 squared plus 3, and then that whole thing needs to be multiplied by 1/2. Now I'm going to stop right there and just talk about what each of these pieces are. Right? This is the function. That's the f. This is the delta x. That's the delta x. Right? And so now what I want to do is I want to start cleaning this thing up. I want to take and do the math here to clean up the argument of that summation and then apply these formulas from up here that we were given earlier. I want to apply those formulas to this problem to find that summation. Right? So again, this is going to still be a summation. This is the summation as I goes from 1 to 8. Right? Oh, but wait a second. Can't I take this 1/2 since it's a coefficient of the entire argument and move it out in front? So let's do that because that's going to be a good thing. That'll make math easier here in a minute. So this is going to be 1/2 times. And see this addition symbol right there? Can I rip this thing apart and write it as 2 summations then? So then this is going to be 1/2 times the summation as I goes from 1 to 8 of 1/4 times I squared plus the summation as I goes from 1 to 8 of 3. So some arrows to see where things came from. This is right there. This is right there. And that 1/2 moved out in front. Now I'm happy with my second summation, but I'm unhappy with my first summation. I'm unhappy with the first summation because of the silly 1/4. But can I take that 1/4 and pull it right to there? So that's going to give me 1/4 times 1/2. I'm sorry, I got my fourths and my halves mixed up. 1/2 times 1/4 of the summation as I goes from 1 to 8 of I squared plus the summation as I goes from 1 to 8 of 3. Okay. Now at this point, since I have my summations reduced down to where I can use the formulas, I'm going to use those formulas. Now because it's too much to go back and forth, over here on the right, I'm just going to copy those formulas down. The formula I need for the first summation says that the summation as I goes from 1 to n of I squared is, I'll go back up and look at, there it is right there. It's going to be n times n plus 1 times 2n plus 1, all divided by 6. The other formula I'm going to need is the summation as I goes from 1 to n of, what they call it, c? Yeah, they call it c. C is just equal to n times c. So now I'm going to apply those summation formulas to my example over here. The 1/2 out in front stays. The 1/4 stays. But this first summation is going to get that red formula over there. So it's going to be n, 8 times n plus 1, 8 plus 1, times 2n plus 1. So that's going to be 2 times 8 plus 1. And then all of that gets divided by 6. Plus, now this second summation there, that's going to get the orange formula applied to it. So plus, well, n times c, that's just going to be 8 times 3, right? At this point, there's nothing left to do but a bunch of math, right? Oops, I made a mistake. Right here, what should that be? That should be 1/4. So let's fix that really quickly. 1/4. Sorry about that. Okay. So let's start doing a little bit of math. The 1/2 out in front I'm going to leave. But let's clean up this first one. This 4 and that 8, that's going to give me a 2. This is 17. This is 9. Okay. So we have 2 times 9 times 17 divided by 6. Okay. So I have 2 times 9 times 17. So 2 times 9 times 17 is 306 divided by 6 plus 24. So let's see, I'm just going to do some math here. Let's see that this is going to become 153 and this is going to become 12. We're just going to get rid of the 1/2. So I have 153 over 6 plus 12. So 153 divided by 6 plus 12 gives me 37.5, or if you prefer, 75 halves. That is the ugliest 5. 75 halves. Okay. So I'm finding the area under the curve. What was our function again? Oh yeah, x squared plus 3 on the interval 0 to 4 using 8 rectangles and right endpoints, and I use summation notation to find it. I get 75 halves or 37.5. So what we're looking at here is summation notation. Now if you think about what we talked about last time, you could probably see what's going to happen. We're going to take this original problem up here. We're going to say 8's not good enough. We need more. So we're going to turn that 8 into a 16 or a 32 or a 100 or a 200 and try to make this thing be more accurate by increasing the number of rectangles. Right? And so what ends up happening is for each of these strips that we're turning into rectangles, if we increase the number of rectangles, they get narrower. If we increase the number of rectangles, they get narrower. As n approaches infinity, then delta x, the width of the rectangles, approaches 0. And that's what we're looking at for. We're looking to find what's going to happen to the approximation if the width goes to 0. Because when the width goes to 0, thin rectangles mean more accurate. More accurate is a good thing. So if this is what we want to do, if we want to find the actual area by taking the limit as the number of rectangles approaches infinity, then we have to take the limit of a summation here. So we're going to rewrite this part of the problem as a summation. And when we write that as a summation, then we can take the limit of the sum. And so we end up with this occurring. We're saying that the summation's limit, or the limit of the summation, is going to give us the actual area if we take the limit as n approaches infinity. So what we ended up with is the definition of the definite integral. The definite integral says find the exact area of the region bounded by the function f of x with a lower limit of a, an upper limit of b. And how do we do that? We do this right here. We take the limit as the number of rectangles approaches infinity, and then this is going to be our height multiplied by our width. Right? Now there are a few things that have to be true for this to work. Our function f must be continuous on that interval for this thing to work. If it's continuous on that integral, then it is integratable on that interval. If it's continuous and integratable, then the area of that region can be given by the integral from a to b of f of x dx. Now you might be looking at this and saying, what the heck is going on here? All this stuff right here is, it's just a mathematical operator. A mathematical operator is just a symbol to tell you what to do. Right? This symbol over here on the left is called the integral symbol. It's a stretched out S. S for summation. It has a lower limit that tells you where to start this area calculation. It has an upper limit for where to stop this area calculation. It has a function to tell you what to find the area under, and this dx over here just tells you what's your variable for your change along that x-axis. So we're working with an independent variable of x. So it's just the pieces and parts that tell you what to do. It's an operator. It's no different than a multiplication symbol or a division symbol. They tell you what to do to perform the calculation. This tells us what to do. It says find the area. Okay. Now, one thing about integratable over here is we're looking for functions f of x that are going to be positive on this, because for this to work, the function needs to be above the x-axis so we can find that area. Okay. So that integratable part here is about being positive on the interval that we're working with. Okay. Later, when we move forward with this, we'll deal with what what we would do if we had a function that was sometimes below and sometimes above, and how we deal with that problem, because that's a different problem. Right now we're going to talk about the ones that are wholly above the x-axis so we can find out what's happening here. Okay. So this is going to be our first example. I'm going to do this in the next video. So I'm going to stop this one here. When you come back for video number 2, we'll take a look at example number 2. We'll actually find the exact area under that curve.